So, good morning and welcome back to the live stream for the lecture visualization or scientific visualization. Behind me, you see a human hand. It's a hand of a person called von Kölliker, and he happened to be a colleague and friend of another person called Röntgen, Johann Wolfgang Röntgen. And today, I want to tell you a little bit how, well, this sort of second ever performed X-ray image came into existence and what that has to do with visualization. So today, I want to talk about measurements, acquisition, and particularly about computed tomography, as it's a nice example how an acquisition method provides data that then is supposed to be visualized by, well, folks like us that do scientific visualization. But first, let's get back to the visualization pipeline. I mentioned it. This is kind of an important concept. It's a relatively simple concept, but nonetheless, it's important. So you see on the top, we get as input various sources, and in particular, sensors is what I'm interested in today. A key point of this slide here, of this visualization pipeline, is that visualization isn't just the stuff here at the bottom, right? It's not just rendering, not just creating an image. As a matter of fact, if you start to actually implement, realize, or use the visualization system, you will notice that the bottom part actually causes least of the headaches and work. So most of the work and most of the intelligence is usually spent in the topmost parts, how to prepare data, how to select what's going to be visualized, and then ultimately render it. Okay, I said I want to talk about CT. CT is short for computed tomography, and the idea is putting someone in a tube. Okay, so in particular, when I say someone, I talk about medical CT. There's also industrial CT, which is kind of the same thing, except that the specimens being scanned are neither humans nor animals, but well, devices, a piece of hardware, a piece of a motor, an engine, well, pretty much anything can be CT'd, I guess. The difference is generally that if you use a material, some sort of metal, a metal alloy or something, you need significantly higher levels of radiation. And that brings me to the next thing. What is CT? What is it made of? Apparently, it's got something to do with radiation. Yeah. CT at its core involves X-rays, or in German Röntgenstrahl. And the actual measurement of a CT scanner is something like this here. That's called a sinogram. More on that in a couple of minutes. That sinogram is then reconstructed into a slice image, which you can see on the left. So that is a typical slice image through a human, human body. And then these slices are then stacked on top of each other to generate a three-dimensional volume. And then what you see here at the top, that is then a visualization of the three-dimensional volume. So ultimately, we care most towards the later part of the lecture, we care most about this. How do we get this here, and how do we generate the thing on top from the data? But as I mentioned in the last stream already, it's crucial to at least know a few details about how the data was generated so that you can appropriately visualize it. You can ignore artifacts, scanning artifacts, simulation artifacts. Those should not be enhanced as features. They should be reduced, removed at best. But at least you don't want to spend any time or computing efforts on maintaining them, unless you're interested in issues in the scanning and simulation process. And you also want to know other properties of the data, like its size, its well, the question that the scientist, the medical practitioner wants to ask, you should also be aware of that, so you can design a visualization that is effective in answering that question. Okay, so I already mentioned that computed tomography and X-rays are related. As a matter of fact, computer tomography is an application of X-rays. X-rays are, well, a new kind of rays. At least they were a new kind of rays, 1895. As many things in science, they were discovered by accident. So Wolfgang Conrad Röntgen, Wolfgang, yeah, I think I said Johann at the beginning. Yeah, it's Wolfgang, of course. Wolfgang Conrad Röntgen, he performed experiments with vacuum tubes and then realized that when he does, in one part of his lab, he does experiments, he noticed that in another part of his lab, he can make a fluorescent screen glow. And then he figured, okay, well, there must be something that travels through space and excites the fluorescent screen. And since he didn't have a clue what this should be, he called them just X-rays, sort of kind of unknown types of rays, and ultimately published the thing. It wasn't long before he discovered that those rays penetrate certain objects. In particular, most of human tissue is penetrated by these rays. So he figured out a way to conserve the excitement, just like in a photograph, where you take a photograph, or you would, before the invention of digital photography, you would take a photographic plate and you would excite that with light. You can also excite a photographic plate with X-rays, and you can develop that to conserve the result. So that is the first X-ray ever performed. It's an X-ray of his wife's hand. So he basically put his wife's hand on a table, including a ring. So this awkward object here is not a pathological artifact or anything. It's or pathological condition. It's a ring she was wearing, and he put a photo plate underneath that. Would use X-ray to focus on the hand and then develop it afterwards. And here we go. So that was December. So pretty much end of the year of 1895. And as you can see, while it's compared to today's X-rays, it's a pretty well low resolution, out of focus, whatever. But well, for a first attempt, I think it's actually pretty good. Or it's the first published one, so they probably had a few failed attempts before that. Okay. So what's interesting about this image is in particular a comparison that you might take to the next image. So remember, this was well, 2 days before Christmas, so end of December. Here's another image of, I would say, significantly higher quality. So it's again an image of a hand. It's again wearing a ring. So I guess they put the rings on because they thought it's kind of cool that you can see the ring around the hand. And that was taken, as I said in the beginning, that's the hand of a person called Kölliker. And that was taken 23rd of January. So just a month later, you can see how quickly Röntgen has improved the method to achieve significantly higher quality. So apparently he was able to focus the rays better and get a significantly better image. And that actually, for medical purposes, for many medical purposes, is probably already sufficient. For instance, to diagnose fractures, to figure out how something is fractured, that would probably do. So they quickly discovered that they're onto something. So later, or today, we know what X-rays are, or we should know what X-rays are. So they're electromagnetic wave, just like light. So here's a small depiction, I think that I grabbed from Wikipedia, of the electromagnetic wave spectrum. I talked about this in computer graphics in a little bit more detail. Here, just the very basic. It's an electromagnetic wave. It's, well, a wave. It's made up of electromagnetic and of electric and magnetic interaction. So, excuse me, two waves travel alongside each other through space, and depending on the frequency of that coupled wave, we give them different names. It's really just humans that give these different waves different names. So there's really no, I would say, inherent physical concept that would say this is light, and then here's where infrared and here's where ultraviolet starts, except that's how our optical sensors, our eyes, work. Okay, but nonetheless, you can see that on the spectrum of either wavelength or frequency, depending on how you prefer to think about it, you see that there's light here, and then if I increase the frequency, you get ultraviolet, and then you get X-rays ultimately. So it's sort of a similar thing to light, except that it's so high frequency that it penetrates tissue. I mean, light also does to some degree. I mean, if you use a high performance lamp, you can actually shine through your hand, right? You've done this before, right? You use a bright LED flashlight and you see how the light penetrates your hand. So the fact that electromagnetic waves penetrate tissue isn't really a big deal. The only thing is that if you just use light, it gets bent and you can't see the structures really properly. Whereas X-rays tend to go, at least when it comes to our tissue, tends to go straight through, so it creates a much better image. The drawback is, well, there's two drawbacks. A, it's ionizing, so it changes our DNA, and B, we can't see it. Okay, so we have to use some special device such as photographic film to well, make it visible to the human eye. How do we produce X-rays? Here's a simple setup. If you want to know more, you can read this up in on the web, basically, or in a textbook, a physics textbook. Just to give you a basic idea how you can create, well, you probably shouldn't, how one can create an X-ray emitter. It's a fairly simple thing. All it takes is pretty much a vacuum tube, pretty much a light bulb plus X. So, I mean, light bulbs have become sort of obsolete recently, but I suppose you still know what a light bulb is, right? It's a evacuated or gas-filled glass tube with a wire in it that is heated up using electricity, and then since it's heated up, it starts to glow. Okay, and that's what we use or used to illuminate whatever we want to illuminate. So if you want to create X-ray, use the same setup here on this side. So this is sort of the light bulb setup. So you use a current to heat this thing up. So this is this UH, this is the heating current. You use this, you apply a voltage, a current flows through this cathode here, and it, or what we later call cathode, and it heats it up. So it starts to glow. We don't really care much about the glow though. But what we care about is that when material heats up, what does this mean? What does heat mean? I mean, heat means you got molecular motion, right? So heat is just our interpretation of how fast molecules jiggle around. And then there's this idea that if you have a solid, the molecules are stuck in some sort of pattern, in some sort of a grid, which makes the object solid. And then this solid object kind of jiggles around. So, and you can actually notice that, right? If something gets warmed up, it becomes softer. You can bend it more easily. Right? So you see that this grid starts to jiggle around. And then at some point, the grid will break apart, and we call this then a liquid. And then if it breaks further apart, it becomes gaseous or plasmic. But if we keep the thing in its, even if it's in its solid form, if it jiggles very quickly, then loose parts of the atoms or molecules, namely electrons, can get kicked out. So you can imagine this here for it's like a game of billiards. So you have those molecules kind of bouncing around pretty quickly. And then if they hit an electron, which has a significantly lower mass than an atom or an atomic core, so it just gets knocked out and then it flies away. What happens is that the electron is negatively charged, and since it's knocked out of an atom, the atom itself becomes an ion positively charged, and then they attract each other. So that creates a counterforce that kind of sucks the electron back. And this process happens very quickly at a bazillion places. So you basically get these electrons flying in and out. Long story short, you create a cloud of electrons flying sort of around this heated piece of wire. Okay, and that's what we're actually interested in. We're interested in these free electrons. Now, what do electrons do? Well, they get attracted by positive charge. So the second thing we do is we apply a voltage, a very high voltage. So here you don't need a very high voltage, right? I mean, you can heat up a piece of metal using whatever, 12 volts, or technically even fewer, as long as you have a high enough current. But let's say that's just 230 volts, or just for the sake of argument, since this is what we use for our outlets here. So this thing glows. Now, at the same wire, you apply an extremely high voltage, right? From, well, here, running out of arm, to here, okay? But there's no connection. So it's just a high voltage, but there's at least at this point, no current, except for the capacitive load at the beginning. So we use a DC, very high DC voltage. And we charge the anode side here positively, and the cathode, and the negative charge is applied to the cathode. So what happens? Well, since those two open ends create an electric field in between, so there's an electric gradient. So we have a positively charged side, a negatively charged side. Okay, so it's a capacitive charge. The free-flowing electrons get attracted by the positive side, and for that, and then they kind of start flying this direction. If this would be filled with air, they would hit objects, air molecules, I guess, nitrogen mostly, right? Oxygen, some carbon dioxide, and they would rapidly stop. However, we evacuate this part here, so it's empty, and then they can flow freely. And what happens is, well, they get accelerated. Since they have so very little mass, they become fairly quick, fairly fast, and then ultimately they hit at a relatively high speed. They hit the anode. Okay, and then something happened that is called, and funny enough, it's both called in English and in German. It's called Röntgenbremsstrahlung. So, which would literally translate into, I mean, X-ray braking or deceleration radiation. And those are X-rays. So the electrons that are decelerated quickly, they lose energy, and that energy is emitted as photons, as X-ray photons. And depending on the speed, the speed determines the radiation type. And if you choose that properly, I mean, you can choose that with different currents and different distances, you get your X-ray, and that's emitted. Just for the sake of completeness, since the anode gets pretty hot in the process, it is cooled from the back. So the red part you see, that's the water cooling. So you generally pump water through this device to cool it from the back. So that's kind of my bird's eye non-physicist view of what a X-ray tube is. And by the way, these things were actually pretty popular in just a couple of years ago, and we call them TVs. So in essence, a TV works pretty much the same, except that the X-rays are an unwanted side effect. Nonetheless, that happened. So this is why TV screens emitted radiation. Okay, so what we can now do is we can, using electricity, we can create radiation. We can switch it on or we can switch it off, which is much more, which is much better than using a radioactive isotope, for instance, right? You could also use a radioactive isotope to create radiation. However, that thing would radiate all the time and you would have to cover it. So it's all kind of a messy process. Here you switch electricity on, radiation flows, you switch it off, and it pretty much stops. A good thing. Now, how do we then get to this image here? Well, you take your X-rays that you can focus into a specific direction that can be done by using that plate where the Röntgenbremsstrahlung happens and designing it in some special way so you can, or shaping it, right? You can make sure that the radiation is kind of focused, and then you can use things such as lenses. For instance, you could use a lead ring as kind of a lens to just focus things further. Or as an iris to focus things further. So, and now if I put my head in the direction of the X-rays, they would kind of go sort of mostly straight through me, except for well, my bones. Bones tend to absorb X-ray to a higher degree than the rest of my tissue, and the rest of your tissue as well, by the way. So bones are significantly denser material. I mean, it's easy to feel, right? Fat, muscle, soft, bones, hard. Pretty easy. So, and dense material tends to block X-rays a little bit better than, or significantly better than soft tissue would. So on the other side of my body, say back of my head, some X-rays are absorbed, blocked, creating mostly heat and to some degree ionizing my DNA. And then on the other side, still some X-ray shoots out, and I can use a chemical plate, photographic plate, that reacts to X-rays by changing the color. So in general, these photographic plates will get darker where they receive more electromagnetic radiation, so they're negative. And then I treat this photographic plate with a development solution and with a fixation solution, and then I get a picture, which is generally inverted. So more radiation means darker parts, fewer radiation means brighter parts, and then you generally change that to a positive to get an image such as this one here, where dense parts are bright and what's the opposite of dense? Well, it's sparse. Well, not so dense parts, let's call it like this for now, will appear dark, right? Well, with that, you can diagnose a couple of things, right? You could, for instance, see a fracture, I guess, but what it lacks is three-dimensional information. Okay, why? Because, well, all we get on the other side of the specimen is the entire absorption level, right? So if a ray kind of goes straight through here, it gets absorbed by my front skull, it gets absorbed to some degree by my brain, very little, but still a little bit, and then it'll also get absorbed by the back of my skull. But I can't sort of tell that apart, which was front, which was back. I just get the total absorption. So it would be better if we could get, well, if we could figure out what's happening in the front and back. So for instance, if I would have a fracture or something, we could figure out where exactly that's going on. So, and for that purpose, we can use computed tomography. Okay, so let's take these two terms apart. So what is computed? Well, I guess I don't need to tell you much about that. That means we do some sort of computation, so some sort of mathematical, numerical magic to get something. Okay, so that's what computed stands for. What is tomography? Topography means cutting things into slices, right? If you take a sausage and then you create little slices, you do a sausage tomography. So computed tomography means we compute a slicing without actually slicing the thing. And I would really appreciate that if someone's trying to figure out whether I have a skull fracture, if they wouldn't first slice my skull and then tell, I guess, the rest of my family what was wrong. That wouldn't help me much. Okay, so we'll just compute a kind of virtual slicing. That's the idea. So what does it take to do this computed tomography based on X-rays? So it first takes X-rays. Okay, cool. We've discovered it. Konrad Wolfgang Röntgen was nice enough to discover these things. Then it takes a little bit of a mathematical magic, obviously, because it's computed, and something developed by a person called Radon was very instrumental in this. So he developed the Radon transform, which we will later on see can be used to perform the computation. Okay, and then I make a leap here, 1972, and notice that this isn't like Stone Age, okay? So we're actually talking about a relatively new technology here with CT. Ambrose and Hounsfield discovered this idea or carried out the first clinical CT. So they had this idea, okay, we can do these X-rays, but we only have this complete projection. Can't we just do something to get the 3D information? And excuse me. And just to give you sort of a basic idea, that is, like I said, if I take a CT this way, I get the projection. Now, what if I would also take a CT this way? Then I would get another projection. And you might have enough imagination to assume that if I have enough of these projections, I might be able to actually do a computation to figure out, okay, what is going on at every point in space, and then reconstruct the 3D volume, which is exactly what the Radon transform describes. That is discovering a mathematical function, or for the matter of CT, an absorption characteristic from a series of different projections. Okay, so that's basically the idea of the Radon transform. So let's look at history a little bit more. Not long after their first discovery, Hounsfield and a person called Cormack, more than that later, received the Nobel Prize. And that's actually a pretty big deal, in particular those days. Receiving a Nobel Prize after a relatively short amount of time, 7 years, demonstrates how important the whole thing is. Then, if we go another 10 years into the future, 1989, something called a spiral CT was first used in the clinic. Again, more on that later, what a spiral CT is. And then at the turn of the millennium, it was a widely adopted technique in the clinical practice. Okay, and it's only grown since then. Well, I guess now every reasonable hospital has a CT scanner, or most larger hospital. Let's put it like this: every certainly has an X-ray machine, but probably most of the hospitals these days also have a CT scanner. So, what is CT? Again, CT is this computed tomography idea of turning this projection, basically kind of flipping it around in a sense. Okay, so again, think about the skull image that I've shown before. So that is a projection this way, and what I want is I want to kind of flip the image around, sort of by 90 degrees, to get these stacks of images, which then ultimately make up the entire volume. So talking about the skull again, what I want is sort of an image that is kind of cross-section this way. So which is what this would looks like. What I've put here together are two images. Well, you can see that's not the same brain, but it's a human brain from 1974 and from 1994. So you see that there's the idea is the same. What happened? Well, a lot of artifacts are gone. So the resolution has increased. We have less noise here, and in particular these artifacts that you can see at the outside. So there are these spiky things. Those are also gone, it seems here, but they're at least significantly reduced. And the devices look a little bit more sophisticated these days. I grabbed this image here from, I think it was a Siemens catalog that I found somewhere on the web, and I put at the bottom here, warning propaganda image underneath. And I guess this here is the source, which I can't read. But the reason I put this in there is like that, okay, they made this look here in the image, well, it's the child's play, right? Put child on it, be fun. So it's still X-ray, right? It's still a CT, still uses a harmful, potentially cancer-causing, potentially, because you never know what's happening to you. But I mean, it's certain that X-ray causes cancer. The question is just what dosage you get, and how it affects you as a person specifically. So it is a harmful radiation, and it's a significantly higher level of radiation in a CT scanner than you would receive in a normal X-ray. Okay, so that should be clear. However, most, not all though, but most physicians, doctors, practitioners agree that there's a ton of situations where the positive effect of getting a clear, almost noise-free view into human body significantly exceeds the risks of radiation. There are, however, a bunch of studies that indicate that a significant, in particular in the US, I know about a couple of studies that indicate that a significant amount of cancer cases might be due to a computed tomography. So don't be surprised if doctors are reluctant to perform a CT and starts with an X-ray first, and then might go this route. Okay, so it's not like you're instantly gonna get cancer, but it's just a thing to keep in mind, just like with any other treatment, or like if you get a medicine, it might have some side effects, and here's the same thing. Okay, the only reason I put this here, this propaganda image thing, is that it's certainly nothing to play with. Okay, so and it's an expensive device as well. So what's happening? So this is usually what you see as a patient or practitioner these days. It's a a thing. It's a somewhat flat device with a hole in it, and you got this slide here that would slide the specimen, patient, animal, whatever you want to scan, would kind of drive this through the scanner. So what's happening underneath this enclosure? And underneath this enclosure, you can see something like this here. So what you get is a rotating object that has on one side X-ray emitters. So that's shown here on the right side. So for instance, these X-ray tubes that I just mentioned. And on the other side, it has detectors. It has devices that can detect X-ray radiation. And then the whole thing rotates pretty quickly and emits X-rays. So what we do is we take conceptually, we take a sequence of photos, X-ray photos, around digital photos around the object. And that's what I said before, right? Take an X-ray from the front, take an X-ray from the side, and maybe a couple more, combine them into one common image, do a transform on that, and recover the whole 3D data set. Okay? So, and then these days, I mentioned spiral CT before, more on that later, but the idea is that this rotation of the X-ray emitter receiver array happens simultaneously to the translational motion. So you shift the patient through the scanner, which effectively creates a path like a spiral here. So if I would look at the position of the emitter relative to the patient, I would get the spiral path here. So this is why we call this setup spiral CT. Previously, you would do a revolution, then shift the patient, would do another revolution, shift the patient, and so on and so forth. So that was kind of the old type of CT, but that's not in use anymore. And I'll also explain why. Just a quick word on how these detector works again. So this is kind of the layman's view here of a physical phenomenon, but it's actually not such a big deal. It's kind of similar to the emitter in the sense that we apply a high voltage to a capacitor in a sense. So you have two plates, an anode and cathode, and in between you have gas, xenon gas usually, and then xenon gas, if it's hit, it's evacuated otherwise. So this thing here is in a tube. It has xenon gas in it. It's a fairly small tube though. So we have this. We have those two sheets of metal for the anode and cathode, creating a capacitor in between. Now, if X-rays hit this tube, what happens is, well, they might hit a xenon atom, and that xenon atom gets ionized, meaning that an electron is knocked out of the xenon atom, creating a xenon ion and a free electron. And these two now get influenced by the electric field because they're now charged. So the electron gets quickly sort of sucked up by the electrical field, so it gets absorbed by the positively charged anode, and then the atom moves significantly slower because it's way heavier. It moves to the cathode, and then the electron, well, a electron, not the, but another electron replaces the excuse me. Replaces the position of the previously knocked out electron. What's going on today? So, okay, nice, you might say. Okay, electron does a few spins. So why would I do that? Because I can measure that current. Okay, so I apply a voltage, and then after the system is charged, after this capacitor is charged, no current should flow unless it gets ionized. So if it gets ionized, if we have an ionized atom, then we see this electron move and we can measure that. Well, maybe not a single electron, but a couple of them can be measured, and that's what you detect. I think actually you can measure single ones if you amplify the signal. But in any case, this can be measured. So we can basically, we have a device here that measures how many X-rays make it through. If you put those in an array, like you do put a lot of those tubes in an array, you can assume that each and every of those is a pixel of a detector, and you get your digital X-ray camera. Okay. So we're good to go. We can measure the stuff, we can produce the stuff, meaning X-rays, and now we can shoot them through a body. Now, if you do this, what you get out is this here, funny enough. So instead of getting this two-dimensional X-ray image from before, this skull image, what we generally do is we just use a slit. So the X-rays are just emitted in a small, thin beam or line. This line, just like a knife sort of thing, cuts through the specimen, cut through this body. We detect it, and then on the back side, we get this, well, single line of pixels. Single line of, well, I guess, absorption or inverse absorption characteristics, right? Where I have, where I see white, meaning not many, I mean, in a photograph, I would see white where there weren't many X-rays. So I would know, okay, well, a lot of it has been absorbed. And where I see dark, well, not much has been absorbed. So from a detector point of view, you would detect a lot of X-rays here, and you would detect fewer towards denser tissue. But the thing is, I just get a line, okay? Now here are some characteristics or sort of state-of-the-art CTs. And state-of-the-art is really hard to quantify here because, well, first of all, state-of-the-art advances. But what's interesting about CT and generally about medical devices, there's a significant difference between what you see at a clinic to what is available in research and development. That is because these devices are extremely expensive. And of course, if you install such a device, you don't want to just buy it and replace it every year. So that would be that would not be very economic. So you basically replace it after a significant amount of usage time, so decades probably. I don't know exact times how long these devices sit in hospital, and I guess it varies from a place to place, but nonetheless, they sit there for a while. Now, compare that to the rapid development that we've seen before. So you might actually have relatively outdated hardware in one hospital, whereas it might be newer in another one. So state of the art is kind of hard to quantify here. But nonetheless, let's say state of the art that you could encounter in a hospital these days are relatively thin layers. So this layer that I said is this kind of slit that you shoot can be relatively thin. So it's sub-millimeter, significantly sub-millimeter. Then from that, and we'll later see how, you can reconstruct images of 2000 by 2000 pixels, fairly high resolution, so that's a pretty high resolution picture. And the units of each pixel in that image are what's called Hounsfield. So we call them Hounsfield units, or HU, or at least the medical folks call them Hounsfield unit. And those units are generally from -1000 to 1000. The Hounsfield units are sort of specific to the medical community as they are normalized to tissue types or to objects that you encounter in nature. So -1000, I put it here, -1000 is the equivalent of air, and 1000 is the equivalent of bone. Okay, so it's just like when you use degrees Celsius, that is normalized to water, right? Freezing temperature, boiling temperature. This here is normalized to human body. Bone being the densest material. I mean, there are different bones, of course, but give or take, some unit bone is 1000, and then the sparsest material, we usually don't have vacuum around our bodies, so we have air, and air still absorbs a little bit, so that would be -1000. And then in the center, they decided to put water. Why water? Because we're made up of water pretty much. So you would expect this to be around 0. Okay, good. So that's the basic idea about Hounsfield. Now we got these Hounsfield thing, and now let's figure out how do we get from, well, these lines, and we capture multiple lines. How do we get to this thing here? So Just a few basic, a little bit of terminology, a little bit basic terminology here. So what we measure, what we measure is the attenuation. So how much is lost? How much do we block? So that's effectively what we measure. What we want, what we want is, we don't want this attenuation, which is a material property. We don't want this attenuation from a certain point into a certain direction. So that's r and the angle. So instead of saying, okay, well, this is a certain angle here and then into a certain direction, that's what we measure. But what we want is like, what is the attenuation here, there, or there? So we want attenuation x, y in a plane, and then ultimately x, y, z if we go to the entire volume. Okay, so we simply need to sort of change the coordinates in a sense here. Okay, and then ultimately you want to create voxels, volumetric pixels, which are picture elements. So a voxel is a volumetric picture element. That's just an abbreviation. So we ultimately want that. What is key here, and now sort of kind of thinking ahead, why am I doing this? Because we want to do visualization. And key insight here is, again, discrete volume. Okay, so to solve this problem, which is a continuous thing, right? A human body or any specimen is a continuous thing. And what we do first to do this reconstruction, to do this change from these two angles, certain emitter angle, certain receiver angle, we discretize the space. So again, we turn the continuous space into something that is discretely sampled. So again, we would expect as a final result, and as a matter of fact, that's the truth, we expect again some sort of a grid, some sort of a discrete lattice, a discrete structure where we're given values, attenuation values at certain points in space. Okay, which is good, good for us as visualizers, visualization folks. I don't know what the term would be, because this is the same as we expected to get from the simulation. So we again get a similar syntactic structure. Okay, so what we get, all the measurements are just for one slice. They're like orthogonal to the actual direction that we're interested in. And then if we can reconstruct one of those slices, we just stack them together and we get the final result. So let's now look at this. How do we do this, sort of flipping things around? Let's start from a very simple type of object. Let's assume we just want to scan an object that is made up of just a single material. Okay, it's made of rubber or water or whatever. Okay, but it's uniform. So it's just constructed of that one material type. Then what would happen if we emit the X-ray on one side? So we emit X-ray here and we kind of shoot the X-rays through. What would we expect? Well, we'd expect this material to, along the line, along the way, absorb parts of that radiation. So every now and then, a water molecule, let's say that's water, a water molecule would influence, would hit, or would get hit by the X-ray radiation, and it would get ionized, and then, well, the radiation is gone. Good. So what happens that, well, there's fewer X-rays on that side. No big deal. What happens along the way? So if I were to plot a function, we would have a certain amount of X-ray radiation starting here, and that would drop. Now, why did I draw a curve here? Wouldn't it make sense to draw a straight line? No, that's actually pretty easy to see. Think about this. So if you can imagine this being like a sieve thing, right? So things get either make it through the hole or not, they get stuck. So what happens if you put something in a sieve, or if you just selectively block things? You would usually block a percentage, right? You would say, okay, well, 5% make it through and the rest hits whatever the grid of the sieve and is stuck. And then if I do the next sieve under that one, or the next layer, again, I filter out a certain percentage. Okay, so I would expect this to be sort of percentage based. And what does it mean? Well, it means, let's say I filter out 1%. Okay, that means 99% make it through, right? So effectively, I multiply the quantity with 0.99. It gets reduced a little bit. The remaining stuff, the remaining radiation, again, gets reduced by 0.99. So it's a successive multiplication along the way of a factor. Okay, and multiplying something successively with the same factor, that's an exponential, right? And then since it's a decaying version, we would probably call it a logarithmic function, right? Because we're interested in it in an exponent in a base that is smaller than 1. So then the exponential kind of look this way, right? So 0.5 0.5, for instance, to a certain power, that would decrease, not increase. Okay, so, but it's an exponential function. So that's how I wrote this here. So I said the initial or the outgoing radiation, it's the initial radiation times some base, and I can change the base in any way I want. I just have to adjust the exponential. So I just say E for convenience sake, E to some power that depends on the material, right? Now, what I'm interested in is that thing that depends on the material. I want to figure out the material. So I compute the logarithm on both sides, or I first divide by 0, compute the logarithm, and then I get this minus rho times d, and this d is how big this is. How often do I repeat this process, right? And now I can solve for rho, or for mu. So I basically, it's not rho, sorry, it's u. I know what the absorption characteristic of that material is, as long as I know what d is. Okay, I need to know d, the thickness, and I need to know what I pumped in, radiation. I hopefully have a clue how much I put in, and I need to measure the outgoing radiation. Okay, good. Now, what's the problem here? Well, a d I can measure, I can measure, and the outgoing radiation I can also measure, but that only works if that thing is made up just of one material, and then I might just pick one piece of it and look at it. Okay, let's see what happens if I've got multiple different materials. Let's say I put one material inside the other. For instance, a metal rod inside a water container, which as a matter of fact is a standard test object that you put into a CT scanner to calibrate it. So if I got a thing such as this one here, or here I have actually air inside a water container. Same thing, similar idea. So I got X-rays going in, and then if I got air in the center, meaning absorbs relatively little, I get a quick absorption. Then not much is happening in the center, and then I got more, and then maybe let's put an iron around it. Then it drops pretty rapidly at the end. Okay, so I get, if I were to measure the distribution here, which I can't because I would have to poke inside, which I don't want to, but if I would be able to, I would get quick, medium, almost no, medium, quick reduction of radiation. But all I get is this value here, and then I hopefully know that value here. So I get a superposition, meaning a product of all of these, or a sum, sorry, I would get a sum of all of these coefficients. So the first reduction, second reduction, next reduction, and so on and so forth. So I can still solve that if I would know a lot of the things going on. So I would have to know all of the absorption characteristics except for one, and then I would be able to solve it. And I would have to know all those D's, all the thicknesses. Okay, so if I would know everything except for one, I could figure that one out. Okay, not a good idea. What happens? Well, how do we generally solve these situations? How do we solve a situation where there's a ton of things that we don't know and they all depend on each other? Well, and that's something that you do in mathematics quite often. We generally just try to do more measurements, right? Or we need more equations that all depend on the same input and that are all independent of each other. So for instance, if you have something like x plus y equals 5, you can't really figure out what x and y are. I mean, you can give me multiple possibilities, but you can't pinpoint it down. However, if I also tell you that x minus y is, say, 0, right? And then you have a second piece of information. And if you combine the two, right, x minus y 0 means they both have to be the same, then I can plug this in and then I figure x and y out. which I think in my example would be 2.5. I think I said x plus y equals 5. Anyways, you get the idea, right? So if I just have more measurements that are independent, right? I can't do the same measurement again. That wouldn't help. But I can do more measurements that all depend on the same variables. And then I could throw those into a system of equations and solve that system of equations. Okay, so how do we get independent measurements? And that's basically the whole idea of CT. So instead of just measuring from one direction, we can measure from another direction. So for instance, by rotating that thing. So for this particular example here where it's spherical, we would still get the same result. But since there are tiny variations, that would give us linear independent measurement. Okay, so we simply need to look from various different directions. So it's an inverse problem. We're given a sum, or it's an integral, but it's kind of a sum thing, right? So we've got this stuff summed up. So we know the sum of values and we want to know the values themselves. So it's kind of an inverse problem. And the Radon transform is exactly this, this transform. So it's this idea, we have a function, given a function, or in particular given, or looking for a function, giving a set of integrals of the function. And in general, you need an infinite set of integrals. You can recover the original function from that set of integrals. And you can imagine this as just solving a system of equations, okay? And as usual, we can approximate the continuous function that would take an infinite set of integrals. We can approximate a certain subset of that function, sampled at discrete points, by a discrete set of measurements. Okay, so we rotate our measurement device by some angle theta, and we measure a bunch of values, and those are given by this detector R. Okay, so we've got our detection line, or generally it's a semi-circle, but we can just assume that it's a line. So on one side we have our little vacuum tubes with a xenon gas that would detect, and we just enumerate them by R. So the first one is R0, R1, R2, R3, R4. So we have different detections, and we do this for every angle theta. So for a bunch of discrete angles, we do a measurement, rotate the thing, do a measurement, rotate the thing. So what we get in the end is we get a bunch of those integrals depending on the angles theta for a discrete set of R's. So for a discrete set of detectors. Okay, before I get to that, let's just assume, or let's just look at what we're doing. Before I get to how to solve this thing, let's just put this into a bigger picture. What we do, or what we could do, is we could do an X-ray image of a torso, right? We would see the lung. So that would be kind of one of those projections. Not specifically because we get these awkward lines, but let's just pretend I do just a regular X-ray. I do this projection from one side. Now, I'm just in the process of explaining this sort of more complex CT process, which would, as I said, would kind of flip this around. So we get a slice through the body, which is along the scanning direction. And then funny enough, what we do in rendering later is we recreate what would happen if we were to do the X-ray in one direction. So we could do this in full 3D, which is a direct volume rendered image. But interestingly, in many cases, in particular in the medical practice, what the doctors do is they turn the full 3D data back into a CT style image. So they do what's called a maximum intensity projection. So you can do a projection into one direction. And you can either do this by summing up, which would give you exactly an X-ray image, or you do it a little bit different, MIP. More on that later, way later in the lecture, what MIP actually is. But bottom line is, you could do a CT to start with. That's my point here. So why don't you do a CT to start with? It's cheaper, and it exposes the patient to fewer radiation. The reason is, well, if you do a CT, you can choose the direction freely later on. You can slice or you can project in any direction. And that flexibility alone is very helpful. So it doesn't always take the full 3D visualization. So that's an interesting insight. So we can do this fairly often. I mean, it decreases a little bit. Medical practitioners get more and more used to 3D imagery, but it's surprising how often 2D images are used, right? But the bottom line is, when you do the full 3D reconstruction, you can choose what 2D image to pick, and you can do this in a computer system. You don't have to scan the patient. That alone is a huge advantage. Okay, now that we know that we do sort of vice versa process from CT to from X-rays to CT, 2D to 3D, and then back 3D to 2D. Let's look at the 2D to 3D thing. So first of all, we flip. That's just a minor thing. We generally flip attenuation and intensity around. So what does this mean? Well, what we get in the measurement is the intensity, how much X-ray is there, and we just turn this into attenuation by saying, okay, well, how much is lost, how much is blocked, okay? Because that's what we ultimately want to know. We don't really care about how much radiation made it out. We care about what exactly was blocked, okay? So this is the first type of transformation that we generally do, and it's this logarithm computation that I mentioned before. So what that gives us is this here, and that is an original result. That's the output of a CT scanner. That is the output of a CT scanner when I scan a slice of a human torso underneath the lungs. So that has things such as bladder, kidneys, yeah, whatever, in it. And as you can clearly not see, well, you can clearly not see that, I suppose. I don't think that there's humans around that can interpret this sinogram thing directly. But what is it? Well, it's a stack of, when I do this full revolution, right? Every time I do one of those CT scans from one direction, I get a line. Now I do the next direction, I get a line, next direction line. And I stack these lines on top of each other to get a two-dimensional image. Here it is. It's pretty worthless, at least if I look at it directly. What would be way more helpful would be this here, right? You can see spinal cord, right? You can see muscle, fat. Well, that works. So the question is, how do I turn the sinogram thing, the stack of lines, into this here? So this is exactly the same data set, what you see here on both sides. And why on earth is it a sinogram anyhow? Why is it such a regular wave? You can actually see, you can easily gather why it's called a sinogram, right? You can spot sine waves here. So that's a dark sine wave here, and then there's a somewhat brighter sine wave here. Why is it made up of sine waves? And how do we get from one to the other? So let's take a very simple situation. So we put a nail. We put just a nail into a CT scanner or a thin wire. Okay, so and I scan this. So, well, what would it do? Well, it lets all X-rays pass except for the one poor X-ray that happens to hit the nail or line. Okay, so if we were to plot this, we would have a spike. We would expect this cross section to be pretty much empty. So no material, but there should be this spike, right? There should be at the point where I cut through the line in the 2D reconstructed image, right? I would expect one point in space where the system should say, okay, well, that is a point where a lot of X-rays lost. Okay, now if I do an image from one direction, right? If I do this image with this thin slit of X-ray, then what happens? Well, I get no absorption at all, no, or hardly any, and then a lot of absorption for a metal, for a nail, probably everything is absorbed, and then no absorption at all. So what I get is just a point, right? In this line, I should see a point, and that's what I put here, top right. So I see a point for scan 3. So, or let's say this scan here, my finger's long enough. So here I see a point, right? This cross section here is a point, and nothing else. Now I rotate my emitter a little bit and I do the next thing. So again, I see a point. So I see a bunch of points. Now, if I stick these points on top of each other, what happens? If you think about the projection direction, what I should get is a sine function, because what I do is I rotate. I mean, I could, instead of rotating the emitter, I might as well rotate the nail, right? So what happens if I rotate an object and look at it, just a single point? Well, it'll move up and down, right? So we got this line here. So what does it do? For you, it moves up and down. For me, it it makes a circular motion, right? Okay, so it just moves up and down. How does it move up and down? Well, that's what the sinus says, right? The sign says, or describes the y-coordinate of a point on a circle. Okay, so for a single point, we would expect a sine wave. Now, what happens if I have 2 points? Well, I would expect 2 sine waves, I suppose, right? What happens if the point is in the center? Well, I would expect just a line. What happens if the point is very far away? Well, then the sine wave has a larger radius, right? It'll oscillate more. If the point is closer, it'll oscillate less. Okay? So I can, so it's no surprise that assuming that a specimen is just made up of multiple points, I should get a superposition of a ton of different sines, right? And that's why this looks like a bunch of sines. So in practice, since we only have finite emitters, we only have finite direction that we scan, this sine wave, or the superposition of sine wave, is sampled, right? It's not just a perfect sine, it's a bunch of measurement points that I then can connect. So we have a finite number of pretty much everything, emitters and direction, okay? So in this is what we call a discrete, because it's finite, a discrete sinogram of the data set. Not that it's any useful for a human directly, but it's very useful for a computer to do what's called a back projection. So this back projection thing is taking the sinogram and turning it into, well, the actual data that created the sinogram, kind of solving the inverse problem, which superposition of sines led to this image, okay? And there's basically there's a ton of ways, but there's 2 obvious ways, I suppose, to solve this. One is to literally throw all of those into system of equations, all those measurements that I did, and solve the system equation. And you can do that. That is perfectly fine. And as a matter of fact, with increasing computational power, this more and more often is used in actual scanning devices. However, there's another approach that is computationally easier and very often leads to better results due to fewer accumulation of numerical error. And that's what's called a back projection, okay? And the idea here is that, again, let's take this simple example. We have this one point that we measure, okay? We've got this one pin, needle, or whatever. And what I get is, like, for each measurement, I get a point, right? So I kind of get, if I would take this point measurement here and would smear that, or basically copy this along my scanning direction, I would get a line. Now I copy another one here, I copy another one here, and so on and so forth. Because I don't know where exactly this happens. So I just assume that I get a constant behavior along my line. Now what I get is, as for these 4 measurements that I did here, or is it 3? 1, 2, 3, 4. Yeah, it's 4 measurements. For these 4 measurements I get here, I get this here as a result, right? I get this star kind of thing. Now, if I normalize the whole object, so I divide it by 4, everything just gets reduced in brightness, right? So I get this one point, which is still pretty bright. Let's assume that my data set contains 1, 1, and all zeros. I get a quarter here, but I get 4 times the quarter here, which is still 1, right? And everywhere else I get 0. Now, if I do more and more and more measurements, say I do 1,000,000 measurements, I would still get 1 here, but here there's only 1,000,000th. So pretty close to 0. So the idea of the back projection is to smear, to copy the data that I get, to take one sinogram line, right? And copy that along its scanning direction. Okay, here's an example with not just one dot, but with a whole data set, a phantom as it's called. The phantom is kind of like a smiley face, right? It's basically two pretty dense, say, iron rods or water rods, other fluids, and then maybe air here. So that's what we call a phantom, because we throw it in a scanner and we know what it's supposed to result in. So if I take just one scanning direction here on the left and smear that, well, it's going to look pretty boring. We can clip it at the outside. So why is it clipped here in circular fashion? Because we know that our scanner is a tube. Okay, so we can cut things off at the boundary. Now, if I take another scan orthogonal to that one, I get this one here. If I take more, I get this one, more. If I take more, I sort of converge towards my smiley face phantom. you still see that there's like artifacts here now outside. Okay, and what are they due to? Well, they're due to these, well, sort of smearing thing that I do, and that it hasn't fully converged yet. And in particular, when are those spikes here particularly visible? If I have something that is extremely high in value, if I have a very high value, meaning something that absorbs data significantly, right? Then I have a peak, and that peak will then also create such a line very prominently, and it'll take longer for the peak to dissipate. If everything is pretty much uniform, this will this will not happen so much. Okay, so that, by the way, tells you if you ever have a CT scan performed of yourself. I suppose a lot of you have. Take a look at the data. You can get it from your doctor. They should give it to you on a CD or whatever. And it generally comes with a simple viewer, but you can also use more sophisticated visualization software that we'll develop here later. You can actually use your own software later on. And you will see if you, for instance, have a head scan performed of the human head, and you have implants, right? You have tooth implants, which are metal, right? They're mercury-based, most of them at least are. So metal is, of course, way more dense than anything else. So you see spikes protruding from your teeth, and that's exactly this artifact from the reconstruction process. Another issue that you can observe is that, well, the detectors, I said, those are vacuum tubes. So they're literally pieces of glass, I suppose it's glass, where there's xenon gas inside, and then xenon gas gets excited and so on and so forth. So they have a certain size, which is comparably big if you compare that to, say, I don't know, a pixel on your CCD or a CMOS scanner of a digital camera, which is really, really tiny. These are comparably big. And there's a problem with this size, and that is that you get averaging, right? We can tell, so when an X-ray hits one of those tubes, we can't tell where it hit. We just know that it hit somewhere, and then we see those electrons moving. So what your apparatus does, what your tube does, it averages things out, right? Over the entire size of your measurement device, you can just tell, well, anywhere in there we saw an X-ray passing through. So you sort of have this detector, which if you think about your data as being a pixel in 2D or voxel in 3D, that attenuation gets spread out to multiple detectors. So we have an inherent low-pass filtering going on. So things get smoothed out by the device itself. And you can try to counter that. Knowing a lot of the details about the device, which really only the manufacturer knows, you can develop a counter function that increases high frequencies. So the very little that is left of the high frequencies that is increased, and then that's what's called filtered back projection. So you apply a filter. These filters are very complicated, very lengthy, and extremely specific to a certain device. So every scanner has its own filtering function, which I suppose is a trade secret generally, or even if you would know it, it would be not very helpful because it's very specific to the setup. And for that one, you can filter a lot of the noise out. You can increase you can recover some of the high frequencies that are gone. So with that one, you can get a pretty decent reconstruction, even with relatively little scans. If you do more and more scans, it'll again get better. But more and more scans means more and more radiation, right? And that's, again, one of the interesting things about CT, and that's what modern CT scanners allow the practitioners to do. So they can say, okay, how much radiation do I want? How much resolution do I want? So you can basically select in a modern CT scanner, how much resolution do you need? Let's maybe put it like this. And how much, as a doctor, how much radiation am I willing to put into the patient to get that piece of information, okay? So, and of course, a doctor should generally choose to do as little scans as possible as to reduce the radiation dosage, okay? So you often, even though the device can do more, you get a worse resolution than possible, but at the advantage of reducing the radiation exposure. So now, Now for this whole helical and sequential thing that I mentioned before. So helical is what I said, you have this constant motion, the opposite is called the sequential CT, and that's what I just explained, the sequential CT. So you do a revolution, you do a bunch of scans, or half a revolution will do. You do half a revolution, you do your scans, you get your sinogram, you reconstruct the sinogram, you get a slice. Okay, now you take patient, shift it a little bit, or shift the get link, but generally the patient is much lightweight than the get link. So you move the patient, you do another scan, you get another sinogram, you do another reconstruction, stack the two together, and so on and so forth. So that's what's called a sequential CT. Works, but has a significant disadvantage over what's called a helical CT, where you put the patient into a constant motion and you constantly scan. So what is what are the two major disadvantages of a sequential CT? Disadvantage number one is you get this, or the underlying idea is that you have this motion, stop motion kind of thing. Okay. Now imagine you've undergone a complicated neck fracture. I guess the last thing you want to do is jiggle the patient around, right? You want to put them into a constant motion, right? Instead of moving them, completely stopping them, moving them, completely stopping them, which is a vibration. Okay. So that's act one. So you probably don't want to do that. Two is a vibration vibrates, right? So what happens if you do stop motion, stop motion, stop motion, you jiggle the object around, right? Humans are generally made up of pretty jiggly tissue. So what you get is in each scan, you might have shifted the patient a little bit, or its jiggly tissue is still in motion, and you again get motion artifact, just like in a photograph, right? If you move something around, you get motion artifacts, unless you have an extremely short exposure. Okay, so. And that is fixed by a spiral or helical CT where you have a constant motion and you constantly scan. It has one drawback though, and that is you don't, like after one revolution or half a revolution, you've already shifted the patient a little bit. Okay, so you basically need to extrapolate from like one revolution and another revolution, you need to extrapolate the slice in between, and that itself can cause artifacts, but the artifacts are way less severe than the drawback that you have from a sequential CT. Okay, so that is today's standard, and it's surprising. Like super modern scanners, they can actually scan extremely high speeds. So that means that modern scanners, which you don't see in a hospital these days, but they actually have very long areas where they just accelerate the specimen and they literally shoot them through the scanner very quickly and then decelerate them. So the thing is actually pretty big because you don't want to accelerate quickly, right? You want to accelerate slowly until you get a relatively high speed, and then you want to decelerate things again. So they can get pretty big, but they scan at extremely high speed to reduce the exposure time to a very short period of time. So and here sort of as a final note on the CT scan, here's an example of what you get if you put an iron rod into a water basin and run this through. So this would be the perfect image here. Notice that it's still pixelated because we have a finite resolution, but we see, well, there's a cross section of an iron rod in a water basin, and then we see the basin itself. Now I just want to show you a few of those artifacts. So here's one artifact, and that is those are the streaks that I mentioned. Okay, so you can see those streaks, and they've been pretty efficiently filtered out on the outside, but you still see them on the inside. And that's what you get if you have, well, a significant amount of difference in density and not enough, scans, or you have difference in the scans, for instance, noise. So this here, this is what you get if you just add noise to the sinogram. Why would you add noise to the sinogram? Well, you don't have to. It adds itself automatically, okay? So that's one of the nasty things about measurements, which in particular computer science often forget. You can't do perfect measurement. That's simply impossible. Whatever you do, it'll always be error prone. I mean, try something as simple as measuring the temperature, right? I mean, I challenge you, go on the internet, buy a thermometer and try to find one that measures at, I would say, 0.1 degrees Celsius precision. Okay, just do it for the fun of it. Try to figure out how much these things cost. So it's immensely hard to do precise measurements, even of something as simple as the temperature. Okay, now this here is even harder. So there's always noise involved, right? And that's what noise looks like, right? It's usually noise that is weighted by the values, and so it's sort of attracted by high values. Here's another one, which is what happens if the number of samples are too small. So if you do too little angles, then you get what's called ringing artifacts, right? You see how things are okay in the center, and then they get bigger and bigger towards the outside. Could be moving blood too. Well, yeah, sure. There's other things as well. I guess moving blood isn't really a big deal for CT because it's a pretty uniform mess under CT, right? You don't really see much in blood unless you use a contrast agent. That's a different story, right? That I'll explain later on. But CT, more on that in a second, is really not very good at discerning different types. So if your numbers of samples, in particular, the numbers of, tubes that you use to detect are too small, you get this here, right? You get like discrete samples and they're just too far apart. If the numbers of U are too small, you get, you get one direction, another direction. So you can separate the direction, okay? And my favorite is the all of the above type of artifacts. Okay, so on top of the ones that I mentioned, you can also have motion artifacts, so things might move around. Okay, so if you shift this iron rod during the scanning process, that's what you get on the top. And there's one type of artifacts that's what I briefly mentioned before. You can get certain artifacts from the extrapolation process of the helical motion. So those are generally stair-stepping artifacts that you can only observe in the reconstructed 3D volume. But in reality, you have noise, potentially too few views, too few detectors, moving objects, and all that combined. And here's a particular example of a problematic case. So that's a person with a hip implant, so proximal femur implant, which is a very common implant type. You have a titanium ceramic implant in the proximal femur, and that of course has a significantly higher density than anything else, and it creates spikes. Another example would be tooth implants, what I mentioned, or any type of implants causes trouble. Okay. So we've had this moving blood question or guess, I guess how Q put it, guess from before. Let's talk about Hounsfield for a few more seconds, and then explain why moving blood isn't really a big deal, unless it expands the vessels and then pushes other tissues around. But those other tissues would have to be something really, really hard, which I guess doesn't happen very often with the vessels. Okay, so we got this normalized scale, Hounsfield units I mentioned before, right? It's the scale between air, bone, and then water kind of in the middle. And the argument I made before is like we're made up pretty much of water, right? So more than half of the human body is H2O, so it kind of makes sense to center it around this. And then the extremes are air around the body, and not just around the body, right? You have significant air inside the body, right? It sometimes has some negative side effects, but right, I'm not just talking about intestine air, but there's also like air in your lungs, right? So you do also have air inside the body. And you have, bones inside the body. So those are kind of the cornerstones. Now, if I'm going to plot the Hounsfield unit to tissue type, okay, so you got bladder, here's a certain type of tumor, liver, so on and so forth. So you get all of your tissue types here. And notice that I plotted them from -1000 to actually 3000. So yeah, they might extend beyond this 1000, which I said is this sort of general bone. So there's some bone. Tooth bones are pretty hard, even if they are not filled with implants. And the hardest bone in the human body are actually the ear bones. So those tiny little bones in the ear are the hardest bones that we have, the densest bones that we have in the human body. And then second are the teeth. So they extend a little bit beyond 1,000. That's just my point. Now, if you look at this one, and notice that I chopped the scale. So that's important to know. Here it's actually, okay, but here I chopped it. So this bone thing actually extends significantly. Okay, that's one thing you should know. This graph here, it starts here. So there's also very sparse bone, very spongy bone in the body. And then this extends all the way to 3,000. All the others terminate way earlier. Okay, so let's ignore bone here. And let's look at this part here, okay? So we got fat, a fat here, mama. We got lung here. Lung is obviously pretty much air, okay? So let's focus on this stuff here, right? So you got blood here, what Q just mentioned. We got blood here. We got the heart. Who would have thought that the heart and blood are pretty similar? I mean, the heart is filled with blood, right? The same is true for liver. Liver is also just a bloody mess, right? So it's some other stuff. Tumors as well. Tumors are generally very well fed. I mean, that's the whole point of a tumor. Tumor is just tissue that replicates at crazy rates. So it's also usually blood filled because it needs, a tumor requires a lot of energy, a lot of nutrition. So bladder is a little bit different. It's a different fluid in the bladder, right? But one thing that you can see, they're all in about the same range. So what's the consequence of that one? The consequence, just draw a line here. So if you draw a proper line here through, then you'll intersect pretty much all of these tissue types. What that means is, well, they will all look the same. Right? If they create the same value, they will all look the same. And that means you can't tell them apart. So they will all have sort of the same Hounsfield unit. You have certain parts of the heart, let's pick the heart here. Certain parts of the heart are different than certain parts of the, say, bladder, right? But then again, so this is obviously different here. But then again, there are parts that are the same. Now, how can you separate bladder from heart? So there's two things that you can do. One, don't be a complete idiot. Like literally, you should roughly, as a doctor, you should have roughly an idea where the heart is located. And you should have a rough idea where the bladder is located. So even though they have the same color in an image, meaning the same grayscale, you can probably tell them apart. Okay, so that's one thing that helps. It's not that easy though in practice. I mean, a particularly crazy example of this, you should know where things are. I mean, of course, there are pathological situations where, I don't know, after an accident or whatever, a birth defect, organs are shifted around like crazy, right? So that might be a situation, but that's very rare. But there are other things that, for instance, are located different from human to human. Okay, so appendix is a good example. So an appendix can actually vary in position significantly and can destroy that exact argument. Like, you know where things are, so you can tell them apart. No, for the appendix, you might not know where they are. So, and then that causes a problem because you see something on where you wouldn't expect it to be and probably associated with the wrong tissue type. Okay, so that is one. So you could say, okay, well, I know where things are, so this is how we can tell them apart. Another solution how to tell things apart is stain them, color them. So how do you color them? Like literally by injecting fluids into the body that have certain characteristic when it comes to attenuation, right? For instance, you can inject gold, like literally gold into the bloodstream. Gold has this advantage that it doesn't do what's the English term? Edelmetall. Anyone can help me out here. So if you can come up with the term or just look it up, right? It's a metal that doesn't interact with anything else. So that's why you would use gold, for example, and that flows through the bloodstream. And then you can detect where that is because it's got a very high absorption rate. And then inert, okay, thank you. Wherever that accumulates, you can see it, okay? And so there's other there's other things such as PET, which is a related measurement technique where you use radioactive things. So you put radioactivity into the body right away, and you detect where that noble metal. Okay, it's literally called noble metal. That's funny. Edelmetall. So it's a literal translation. I would never have guessed that. So anyways, so you can inject certain colors, so to say. Well, they're not colors in a sense as we would think about colors, but they interact with X-ray, not light. We call them contrast agents. So you inject a contrast agent into the body, and then the contrast agent hopefully is not poisonous or not too poisonous. And then it hopefully also makes its way out of the human body sooner or later. And that's another way how to distinguish different types. But certainly blood from organs is very hard to distinguish, hence motion of blood is no big deal. In particular, you can't use CT to distinguish anything inside the bloodstream, at least not at under normal conditions. Okay, so there's again in vitro CT where you take small parts of the tissue, maybe just a vessel or just a blood cells or blood itself, and then you make specific settings to CT, so make it very sensitive, for instance, use very little radiation, and then just scan parts of it. Then you might be able to detect differences, right? But not in vivo for an actual patient. So one thing, just to get the vocabulary here straight, is windowing. So that's what doctors refer to, highlighting different parts. So we would call this scale and bias. I guess computer scientists would just call it scale and bias. Doctors call it windowing. Okay, so we got a very long question here. The Meyer law of attenuation coefficient depends on frequency. Do different X-ray wavelengths observe different Hounsfield scale, or is there like optimum? That's a good question, and I frankly don't know the answer. So your first part is correct. So of course, different CT frequencies have a different result. But if there's like an optimal frequency that is chosen, or optimum X-ray, I don't know. Frankly, I don't know. But my guess would be that since you normalize Hounsfield unit to specific tissue types, such as air, water, you can probably normalize a lot of that out. But I know that you cannot transfer results from one CT scanner to another. So you should always stick with one CT scanner when you do comparative studies. So there is a difference. How big the exact concern is, it's hard to say. I mean, I don't know this. I'm a computer scientist, right? I just know that it's an ionizing radiation, so it's probably not good for your DNA. How big of a concern that is very hard to answer. I mean, I know that science and medicine is struggling with this question for quite a while, and I don't think that there is a definitive answer to that. There's just this very simple thing, which I guess is true for anything that is related to cancer, is the fewer the better, right? But that doesn't necessarily mean that when you undergo a significant radiation dosage that you automatically get cancer, right? Take incidents such as Chernobyl, for instance. So there are some people that survived high dosages and still live to this day healthy. And there's other people that die of cancer, even though they received significantly lower dosages. And it's kind of an open question, how much is a good idea. But generally, the fewer the better. So this is why you normally keep track of how much X-rays have been performed. You keep track of how much CTs have been performed for every person. And every doctor should make a informed decision of how much to do this. I just know of this study. I could dig it up. So if you're interested, send me an email and I'll try to dig it up. The study that says that a significant amount of cancer cases in the US might be related to CT scans. But then again, since it's a process that doesn't happen immediately, it's very hard to draw a conclusive to get a conclusive answer. But that is actually pretty old. I don't know of any newer results. CT is still in process. CT is still being used. There are some alternatives, which would sort of be my finishing remark, and we're on time anyways. So there are some alternatives that are less harmful. A more modern, since it's newer than CT, scanning modality is MR, magnetic resonance imaging, so MRI in full. So MRI uses magnetic fields, which as far as we know, aren't harmful to the human body, at least not permanently. So they might interfere a little bit with your sense of what is it, Gleichgewichtssinn. So there might be some interference, but it's only momentarily. So MR is generally considered to be not harmful. But trouble is MR is way noisier, way noisier. The resolution is significantly lower. It's way more expensive. It takes significantly longer. It's super loud, but okay, well, you can, that's okay. Well, yeah, it's just a more modern thing, and it detects different modalities. So MR basically detects bipolar molecules, essentially water, and CT is based on absorption characteristics. So so it's different, and then there's of course ultrasound as another alternative. So I guess there's a slight push, as far as I can tell, in the medical community towards first doing other scans and then using CT. Okay. Yeah, so this is an interesting point since you bring this up. This whole 8-hour flight argument, right? So this is something I don't think it's a tenth of a CT. As far as I know, it's a little bit less, but again, it depends. It varies from CT scanners to CT scanner, so they get better and better reducing the dosage. But anyways, it's a certain amount. Let's just say it's a certain percentage of a CT scanner. Never mind the exact numbers here, but that is underestimating how harmful a transatlantic flight is. So I guess that is something that you shouldn't forget, right? I've seen this argument a couple of times. It says, okay, well, if you do a transatlantic flight, you get, say, let's maybe stick with your 110. You get a tenth of a CT scan. So if you do 10 flights or 5 flights back and forth, you're about at the level of a CT scan. But and there's two conclusions you can draw from that. One is, oh, CT is no big deal, or maybe I shouldn't fly that much. And you should take both of these into account, okay? So yeah, radiation, flight radiation is also harmful. Cockpits are shielded better than the rest of the cabin, so for a reason, okay? So yeah, you shouldn't underestimate, you shouldn't overestimate it either, right? So if you're like that's one thing that I should probably get clear here. Okay, so if your doctor wants to perform a CT, they do this for a reason. Okay, this is for a reason because there's a significant health condition that you're in. So and they do take all of this into account. So it's not like a thing that you should avoid at all costs, right? No way. But it's just something that doctors do take into account. So they're higher level of cancer in flight attendees. And yeah, I mean, there are also higher level of cancers in whatever people that eat food A or food B. So it's all a statistical thing. And that's the big deal about cancer. It takes a while to develop. It's all a statistical thing. It's different for each person, right? You can just do a more or less educated guess over a large population. So it's really hard to say what happens. Okay, but back from all those medical things that I know very little about. So again, be very careful. I'm a computer scientist here. So this is all about visualization, right? If you want to know details, you should probably talk to a radiologist. Certainly talk to a radiologist. Okay, but I can just give you kind of the basic overview. And what's the basic overview? That a CT scan is from a syntactic point of view similar to an MR scan that I mentioned. And again, MRI, if you want, look this up. It's based on magnetic fields. It's a little bit more complex, but again, it's something that it's not too hard to understand. But it gives you a characteristic of a magnetic response in the human body, and it gives you in particular, and that's the interesting part from visualization, it gives you the same type of data. So the data representation, which will be the next topic, next stream, is the same for most medical, or for a lot of medical scans, such as CT or MRI, or PET for that matter. also for simulations that I mentioned before. So what is our take-home message here from the first two actual streams that contain information in this series is that we get data on a grid, okay? And that grid is either based on a simulation, because we want to do a numerical simulation, or it's based on finite measurements that we do. And that is not just true for medical input or for flow simulations, but it's also true for a lot of other types of input data that we get. And knowing where the data comes from tells us, okay, what are the frequency characteristics of this data? Okay, so for instance, thinking about CT, thinking about those artifacts, that's why I mentioned them. Okay, if we have spherical artifacts, we shouldn't spend a lot of resources in enhancing them as features of the data, but more on suppressing them as being artifacts from the acquisition process. And this is why parts of this are important when you do the visualization. Technically, whether that causes cancer or not is none of your concern if you just do the visualization, okay? But what is important is how is the data structured? What is an artifact? What is a feature? Okay, with that, we're done for today. Next topic, next week, will be about how do we represent data, how do we filter data, how do we process data to then ultimately look at it. When will the current semester's video be available? Right away, I guess is the answer. You should be able to, on Twitch, since they're preserved for 2 weeks, you should be able to watch the videos, and I transferred them to YouTube as well. So they should be in the YouTube playlist as well. But this, for now, it's the same, right? I mean, it's just that after 14 days, Twitch videos will get deleted, but the YouTube videos will stay there. I can double check whether the YouTube playlist has been updated. It should be. I think it's in the playlist, but I'll do another check. Once this is done here, once this video is completed, I'll upload it to YouTube. Yeah. Okay, so then, I mean, we only had 2 so far. Then the second one is, it's already copied to YouTube, but then it's probably not visible yet. And here on Twitch, you should be able to at least see the video from last week, which is really the first one that contains information, and the one before that was just introduction. Which makes sense, right? It's 14 days, so it probably has been deleted today by Twitch. Okay, anything else? Do we have any other questions? While I get something to drink. Okay. Okay, doesn't seem to be the case. Then that's it for today. Again, next stream, which is next week, if you watch this live, will be about how do we represent this data? How do we, well, turn it into something that is useful for the following mapping and rendering stages. Until then, as usual, bye-bye. Have a nice remaining week and stay healthy.